How to interpret FRF4 vibration modes. If you have ever wondered how mechanical systems respond to vibrations, you are in for a treat. Understanding the frequency response function, or FRF, is key to grasping vibration modes. The FRF is a powerful tool that reveals how a mechanical system reacts to sinusoidal excitation across various frequencies. To start, the FRF is defined as the ratio of the output response, which can be displacement, velocity, or acceleration, to the input force in the frequency domain. This function consists of two main components: magnitude and phase. The magnitude part shows the amplitude of the system's response at each frequency. When you look at the magnitude plot, sharp peaks indicate natural frequencies where the system resonates. This means the system vibrates strongly at those frequencies. On the other hand, the phase component indicates the time shift between the input and output signals at each frequency. This phase information is essential for distinguishing between different vibration modes and understanding their relative motion. Now, let's break down how to interpret the FRF4 vibration modes. First, identify the resonant peaks in the magnitude plot. Each peak corresponds to a natural frequency of a vibration mode. The height and sharpness of these peaks relate to the mode's damping and energy dissipation. Next, examine the phase behavior. At resonance frequencies, the phase typically shifts rapidly by about 180 degrees. This phase plot can confirm resonance and indicate mode coupling or complex dynamic behavior. To determine mode shapes, measure FRFs at multiple points on the structure while referencing them to a common input location. This method allows you to extract mode shapes, showing how different parts of the structure move relative to each other during each vibration mode. For example, some areas may vibrate with high amplitude, known as antinodes, while others may show little to no movement, called nodes. Assessing damping is also important. The width of the resonance peak and the rate of phase change provide insights about damping. Narrow peaks indicate low damping, meaning sustained vibrations, while broad peaks suggest higher damping. Using experimental modal analysis, you can process the FRF data to extract modal parameters such as natural frequencies, damping ratios, and mode shapes. This characterization is vital for understanding the system's dynamic behavior. Interpreting the FRF helps mechanical engineers design structures and machinery to avoid damaging resonances. It also aids in optimizing vibration isolation and improving reliability. For instance, in rotating machinery, identifying vibration modes through FRF analysis allows engineers to predict and mitigate resonance that could lead to fatigue or failure. By analyzing the magnitude peaks to find natural frequencies, studying phase shifts to understand dynamic relationships, and combining multiple FRFs to visualize mode shapes, you can gain a clear picture of how a mechanical system vibrates. This knowledge enables effective vibration control and design optimization.